Welcome everybody to this fourth edition of the Hitchhiker's Guide to Rheology. I'm sorry.
Rheology.
And let's welcome Holly Bridge, currently a PhD student at the University of Edinburgh. So the first speaker of this last edition. And the talk is going to be about curved into a corner, how particle symmetry controls flow and rest in rod touring suspensions. Holly, the floor is yours.
Thank you.
And maybe before you start presenting your work, can you give us a few words about your background? Where did you studied, and what you want to do later?
Yeah, absolutely. So I did my master's at the University of Leeds. So that was an integrated master's. And then I started a CDT, which is something that we have in the UK where it's a PhD program where you do kind of, let's call it extra training alongside your PhD and your research. So for that, we moved as a cohort to Durham, where we work with companies on industrial solutions that are based in soft matter physics, chemistry, and biology. So we work kind of in an interdisciplinary team. And then after we complete that training, we pick a host university. I picked the University of Edinburgh, where I'm in the physics department, which is still a soft matter department. And that's why I look at dense suspensions, which are, part of the soft matter community of physics. So yeah, I don't know what I want to do next. That's the answer. I'm still quite open. I'm in my final year. I've got around a year left until I need to hand in my thesis. So I'm still quite flexible to what the future holds.
Nice, nice. Okay, well, thank you so much. As I said, the floor is yours, and Holly prefers to get questions at the end, possibly. Otherwise, you can also write them in the chat. And so, yeah, please.
Can you stop sharing your screen or
Yes.
thank you very much. Let me just double check that you can see. So
Yep.
can Yeah, you see perfect. that okay? Yeah. And if I flick, is that still visible? Yeah,
Yes.
brilliant. Yes. Okay. So as I said, I work at the University of Edinburgh. I'm in the soft matter physics department, and what I work on are curved rods in dense suspensions. So when we think about the rheology of collections of rod-like objects, a few different images might come to mind. So these might be entirely natural. So for example, a bird's nest. This is a messy but remarkably stable structure. It's built from these long aspect ratio twigs that are arranged uh, together purely by geometry and contact. And through this, the network is locked into a mechanically rigid state. And I use this example first because it's familiar and one of my favorite examples of a jam state where stability emerges from the way that the many rods restrict each other's motion. And I'll talk more about jamming later in this talk. Another, sorry, one second. Another example might be synthetic. So, yeah, no, sorry, I thought I'd flick to the next slide. We could look at an entangled hydrogel filaments that are 3D printed. And these are originally randomly orientated, but when they're subjected to high pressures and extruded through a nozzle, we can see that they orientate with the flow. And so their mechanical behavior is underpinned by how they orientate and align and slide past one another when the network is sheared or stretched. So in this talk, I want to kind of use this perspective to motivate rod-like rheology and how rigidity, curvature, and these orientation dynamics shape material behavior. And I'll also briefly talk about some biological applications of this. So when we think about rod-like rheology, it's useful to begin with the simplest of cases, and this is spheres. So granular packings of spheres or even something as simple as a pile of oranges in a supermarket. These are systems that we understand rather well, but nature and engineering rarely give us these perfect spheres and perfect systems. So many materials are often composed of anisotropic particles. And when we move from spheres to rods, we break symmetry and suddenly orientation matters. Rods can align and entangle and interlock, and this will produce qualitatively different states of matter. And if we go even further from uniaxial rods, of which we've seen some work in recent years, to biaxial rods, this phase space becomes even richer. So particles not only have length, but now they have intrinsic curvature or secondary axes of alignment. So while spheres have given us this clean foundation, it's the broken symmetry of rods, and especially biaxial rods, that opens up the diverse and complex rheological behaviors that I'll focus on in this talk. And I also, every time I give any talk, I highlight that this work was largely inspired by a study done by a group that was in Oxford at the time, who had an experimental system where they investigated these curved rods in a quasi 2D system, and they saw that at high volume fractions, this vortex phase formed. So this was the inspiration for us looking at biaxial particles to be like, hopefully we see something great and something interesting in a dense suspension. So I'll just give a like a whistle stop tour through dense suspension physics, or what's relevant to my results, in case people aren't familiar with the dense suspension side as opposed to the granular side. So on the left is an image of a dense suspension, and it's specifically glass beads and glycerol, and we can visibly see that it's quite viscous. So if we take a closer look into the microstructure of this, we can simplify it down to solid particles dispersed in a liquid solvent. And what's kind of important about this system is that it's a non-Brownian system, and we can prove this by just looking at the kind of Einstein's diffusion relation, whereby we can show that the diffusion timescale is long compared to timescales of flow or rearrangement when we look at the particle size. So in other words, when we're looking at this system and when we're modeling the system, which is what I do because I'm computational and this work's computational, thermal motion is negligible. And then when we subject this system to mechanical stress or shear, we often measure this reduced viscosity. And I always like to highlight that this reduced viscosity is directly proportional to these particle stresses, because when we shear this network, we can kind of see in the diagram here, I might be able to use a laser pointer. Hopefully you can see this. You can see that as we shear the network, more particles will come into contact. And so we'll see this increase in particle stresses. And therefore, this is what we talk about when we talk about reduced viscosity. So I like this because I like highlighting this because it provides a direct link between macroscopic rheology and microscopic particle interactions. And so if we think about this transition between hydrodynamically dominated systems or mediated systems and then contact dominated systems, we can kind of think about the microstructure I just showed like this. So if we increase the volume fraction, you can see that with these diagrams here, more of these particles are coming into contact, and then at a characteristic volume fraction or nearby, we can see that these networks start to form, which is shown not so clearly with the gray particles, but then here we have an example of the contact network shown in orange, where the thickness of the lines is just the magnitude of the forces. So if we measure viscosity against volume fraction, we see that as we increase the volume fraction, we transition between hydrodynamically mediated interactions to contact dominated, and that's what jamming is. So that's when we have the characteristic volume fraction at which we see that this system no longer flows because this network causes a rest. So that's a big part of my talk today. So I just wanted to walk you through the physics of that. And in terms of the interest of uniaxial systems and jamming, we've seen that people have looked at, I do believe that this is silica rods in glycerol. So this is a suspension, it's not a dry granular system. And when they look at this viscosity against the packing fraction, we see that these larger aspect ratio rods jam at a much lower volume fraction than spheres. And and we can start to wonder at this stage why this would occur. And this is, the basis of a lot of my analysis. So, and in terms of interest via simulations, I haven't seen definitely biaxial work, but we've seen some uniaxial, dry granular, and I'm sure now some more dense suspension. So with your background fluid, computational work whereby computationally it's a lot easier to model a continuous variable of aspect ratio. So when they vary aspect ratio, we see the same relationship whereby increasing the aspect ratio decreases the jamming volume fraction. And what's quite interesting is that in straight rods, we've seen that this is a monotonic relationship. Okay, so now to jump into my work, I'll only outline the minimal model, but at the end, I welcome questions about the model in more detail. So as I've said, we have to model particles as non-Brownian because we have a dense suspension, and we just use simple shear flow. And we represent curved rods as chains of beads connected by stiff harmonic bond angle and dihedral potentials. And this, individually, the bond potentials prevent unphysical stretching, the angle potentials set kind of the preferred curvature and resist bending modes, and the dihedral potentials suppress twisting. So if we ensure that these are stiff, we preserve the rod's 3D shape. So together, these stiff constraints ensure that the assembly behaves as a nearly rigid rod with a fixed intrinsic geometry. And in dense suspensions, hydrodynamic interactions are dominated by viscous effects arising from mainly the motions of closely spaced particles through the fluid because we're in the dense regime. So to capture these effects without explicitly resolving for the fluid flow so that it's cheaper, we employ just a simplified hydrodynamic model, which is based on Stokes drag firstly. So this just represents the viscous resistance experienced by a single particle moving through a stationary fluid, and it's proportional to velocity, shown in the equation. It doesn't imply a two-way coupling, so the background fluid doesn't evolve in response to the particle motion. And then we also model lubrication forces. So this captures the dominant short-range hydrodynamic interactions that arise when the particles approach close contact. So we don't model any long-range hydrodynamics. And importantly, lubrication forces resist relative motion, and they diverge as the interparticle gap narrows. Okay, and then finally, as part of the minimal model, in dense suspensions, particles frequently come into contact, and so we just use simple Hookean contact forces to provide just a simple and effective way to model short-range mechanical interactions. So when two particles will overlap slightly, when they're nearby, we just have the linear repulsive force, which will be proportional to that overlap distance, and that just acts to restore separation. Okay. So again, if you have any questions about the model, please ask at the end. So what does this look like? Let's start with one configuration first. So these are curvatures of 180 degrees. This is, I've shown on the left, it's a fairly dense system. I've shown 25% of particles that are visible. And I just wanted to highlight that. So when we have this system and we want to look at certain mechanical behavior, what we do, like I said earlier, is we look at the dynamics. So we have the reduced viscosity here on the y-axis, and then the time or this accumulated strain on the x. And what we need to do is, for I look at in terms of mechanical behavior, we need to find the steady state viscosity for each of these volume fractions. So in the color bar here, you can see that these different colors represent an increase in volume fraction. And we can start to see here that when we increase the volume fraction above 0.4, which is what this image corresponds to, we see a jump in the viscosity. So if we look at all of our configurations, from 0 to 360. And each of these points here is a steady state viscosity as shown from the previous curves, whereby these points are actually an average over 3 realizations, where they are initially orientated in completely random orientations, so different C values. And the error bars are shown with the bands. So we can see that if we do this, if we get the steady state viscosity for each volume fraction for each curvature, we see this divergence for each of these configurations in a range of about 0.4 to 0.46. But what's not so clear is the relationship between the curvature and this jamming volume fraction. So what we do is we take the divergence of each of these curves, and then we just plot the jamming volume fraction against the curvature. And this looks like this. So we can see that the jamming volume fraction is a non-monotonic function of curvature. And I think sometimes that this is a little, maybe I'm biased, but I think it's a little hard to digest this figure. So we can kind of break it down into, we can see, straight rods jam at a lower volume fraction than small curvatures. And then we see an overall trend in as we increase the curvature, the jamming volume fraction decreases. We kind of have this plateau for these intermediate curvatures. And then as we kind of close the loop, which is something I say in terms of we increase the curvature from 315 to 360, we see that the jamming volume fraction jumps up a little bit again. And we can suggest a few things about why this might happen first. I've done some recent work on exploring, whilst this is more of an open talk, I just thought I'd put in kind of some preliminary results as well. So for me and my team, it's not quite clear as to why a small curvature above a straight rod would allow this volume fraction to jump up. It's kind of, does breaking the uniaxial symmetry a little bit allow curvatures to align better? So what we've done is recently these are just a singular realization for each point, which is obviously shown by the error bars being a lot larger. We can see that if we look at intermediate curvatures in between this range, it isn't a linear increase. We just see that it jumps up at kind of a characteristic small curvature. So we're looking into that a little bit further and suggesting why that might occur and why just that small curvature allows the system to suddenly reach better alignment, better packing, or whatever it may be, which I'll talk about a little bit more later. And then similarly, what I said about how when we close this loop, we also see that the jamming volume fraction jumps up again, which it was quite surprising. And when we measure these intermediate curvatures once again, we see that a similar situation where it jumps up, it seems, the jamming volume fraction, that is, at a characteristic volume fraction. So we can kind of say, does reduced interlocking, that was my first kind of postulate. Now that we close the loop, does that result in better packing efficiency? And I do touch upon these postulates and these hypotheses a little bit more later, but it's definitely something that we're trying to explain a little bit more in detail as opposed to the overall trend with the jamming volume fraction against curvature. So with that in mind, what can we measure? Well, and what have we analyzed? So hopefully you can see those videos. I've just picked 3 key curvatures, and I kind of keep this theme throughout the presentation because we have a straight rod, a very curved rod, and then a ring. And what I like to say is we can suggest what mechanisms may be at play or dominate the jamming transition and explore them. But what we can also do when we model these systems is just visualize them and watch them and see things that we know and identify them and then measure these things. So I might play the videos again so we can look at these 3 or all of the visualizations and start to pick out dynamics that we see that we think would affect the jamming volume fraction or the rheology of the system. And certainly in straight rods, it's very clear that we know that uniaxial particles will align with the flow. We see this visibly for our for our visualization of straight rods. Um, but is it so clear when we look at biaxial particles which primary axes of these rods aligns with what? Does it align with the flow? I think there's been some work into biaxial particles in terms of their singular dynamics, in terms of dense suspensions, which are much more rich. Um, we start to suggest things, and then finally, rods are uniaxial, but still we can see clearly different alignment dynamics to what we can visually see with rods. So we can ask two primary questions, and I hope that I answer these to some degree in the following slides. How does the degree of alignment affect jamming, and also how do biaxial particles align with the flow? And to do this, we first needed kind of a universal shape descriptor for these particles. And identifying the primary axes of uniaxial rods is fairly simple, but when we look at biaxial rods, it may not be so obvious. So we can use the gyration tensor, which is a shape descriptor that is just solely based on particle coordinates. So it's quite cheap to compute in terms of when we have these highly dense systems. And what this does is it helps us identify the primary axes of the rods. So from the three eigenpairs, the largest eigenvalue is the long axis of the rod. And for this presentation, we denote this as U. So we can see that it would be identified as this for each of the rods. And then the second largest eigenvalue with the corresponding vector v, which again, we'll keep this notation for the rest of the presentation, I show in red. And then finally, the out of plane, or the third axis of the rod, as w, which I didn't show because it was just a little bit neater. So if we do plot the values or the magnitude of lambda 1 and lambda 2, we can see that as we increase curvature, as we expect, the long axis decreases and the short axis increases until they converge for 360, where these two eigenvalues would be degenerate. So we can see that the gyration tensor identifies what we meant for it to identify. And so we use these vectors in our analysis. So as I said, we want to look at the alignment dynamics in the system. And to do this, certainly the granular community, but many communities use liquid crystalline theory to do this. So the Q tensor allows us to measure the average alignment in the system, and we can specify that this measurement is to be taken on the long axis of the rod. And from this, again, we get the three eigenpairs, and importantly, the largest eigenvalue corresponds to the magnitude of alignment of the rods with one another, and the corresponding eigenvector is the director of this alignment. So what does this look like? In this part of the talk, I don't want to gloss over some really rich dilute dynamics that we've observed. So I have a few slides talking about kind of volume fractions of 0.1, which you can see here from the color bar, and then 0.25, because it's really rich in terms of curved rods. So yeah, I just want to highlight that this is a more dilute system, and then I'll kind of jump back to our jamming and high density system again. So here we plot order SQ against time, and we can see that over quite long strains, so much longer than what the strain that the system, the magnitude of the strains that the system needs to reach steady state viscosity, we can see this oscillatory behavior for all three curvatures, all of these three curvatures. And we can see that there's a relationship between this oscillatory behavior and the curvature. So we can kind of suggest, based on certainly what we showed in the gyration tensor, that if we see that the frequency for sure increases as we increase curvature, then we can suggest that this is due to the rotation dynamics of the system, and this is an aspect ratio effect. And if we think about rotation dynamics and aspect ratio effects, we think of Jeffrey orbits. So we can actually break or we can understand more about why these oscillations occur by looking at the Jeffrey orbits, because it's not entirely trivial as to why these oscillations occur collectively in the system at dilute volume fractions. So a small caveat is that Jeffrey orbits are the motion of one rod, and obviously the order SQ is a magnitude of the system alignment. But we can still compare the kind of periods between these oscillations and the Jeffrey orbit to see is this system collectively rotating together, and this is why these oscillations occur, or is it a little bit more complex than that? So we can see that the periods are and certainly for a straight rod are certainly in agreement, but we can see that the collective dynamics. So for the straight rod in the dense suspension, we can see that the period of the oscillations is much smaller. So we can start to suggest some things about if the rods collide coherently with kind of the rotating domain, the mean rotation period of this becomes shorter than the single particle Jeffrey period, because we have kind of this hydrodynamic and steric coupling, and this shifts this period to a slightly smaller one. If that's not so clear, because we're still in the process of analyzing this system, I kind of thought I'd take one slide to kind of break down for the straight rod why we think we see this damped simple harmonic motion in the system alignment. And then I'm just going to look at straight rods, for example. So initially we have a random orientation, and that's why we see that the order of the system is zero. And then as we apply the shear, we see that rods will collectively align together with the flow. And this is why we see this kind of increase. And we also see that this is the same rate for each curvature. We then see that we have this Jeffrey orbit dominated rotation collective dynamics, and the rods will tumble. And then as we have these increased collisions, the rods are going to decohere. They almost come into contact and knock each other out of these Jeffrey orbits. So we believe that this decoherence of this collective motion is why we see this oscillatory behavior. And then we see that once again, after kind of a dissipation of this decoherence, I would say, over long times, we see that rods will align collectively again. But we see that this is of a lower order, than the previous collective alignment, because the directions of rotations will be spread out after the collisions, and this means that the Jeffrey orbits are out of phase. So we're doing a lot of work to kind of unpick these dynamics, and what is quite promising, but we would expect as we increase the volume fraction, we see the same initial peak. So rods will align collectively together initially, and they're in phase, and then we see that as they come into contact, instead of this kind of dephasing the Jeffrey orbits collectively of the system, we see that these contacts at this kind of intermediate volume fraction just allow the system to almost hinder, like the rods will hinder one another, and therefore they just reach this steady state alignment. So initially we have this collective alignment with the flow, and then as rods come into contact, they can no longer rotate or continue to rotate, and that's why they just hinder one another in this alignment with the flow. So we can think about this, or something that I like to compare it to is these collisions cause an irreversible kind of dephasing of the rotation dynamics. And I like to compare it to, say, an inverted sand pile. So it's easy to collapse. So when they start to come into contact, this collective rotation behavior is now collapsed, and it's really hard to rebuild because the rods are randomly out of phase, and it takes many strains certainly at low volume fractions for these to become, if ever, in phase again. So I just wanted to walk through those dynamics and certainly open the floor later to any questions or any suggestions about this. So if we look at a dense system, so this is at volume fraction 0.4, then we can see that the oscillatory behavior is dampened, and we just see that we shear the system, the rods collectively align, and then they reach this kind of steady state order. And then I've kind of walked us through each volume fraction here, and said that it holds true, which it does for each of these curvatures. But I think when we show these three volume fraction regimes all in the same graph, we can certainly see that this behavior holds true for each curvature. So we see that oscillation occur in the lower volume fractions, and then it's gradually dampened at the higher volume fractions. And certainly as we increase the curvature, so this is straight rods 180 and 360, there is a clear relationship between the curvature of the rod and these rotation dynamics. So if we wanted to unpick this a little bit further and the rotation dynamics a little bit further, we then look at all curved rods together. And I know that this is a pretty intense, or I mean, it's a busy figure. But what I want you to kind of take away from this is again, when we increase this curvature, we're seeing a clear relationship between these oscillations. So again, this is kind of flicking back to the dilute system. We see a clear relationship between these oscillations and the curvature. And when we look at even longer strains, it takes a long time for these oscillations to reach or dampen out completely. So we wanted to analyze this a little bit further. And when we look at this figure, you might think, well, this is damped simple harmonic oscillations. So we fit that equation to these curves, and then we can pick out the parameters more quantitatively, which will kind of prove what we can visually see. So to only discuss two parameters, because I'm aware that I don't have too much time left, we can pick out amplitude from the damped simple harmonic equation, and we can see that so we're looking more so at this slice here, we can see that as we increase the curvature, the amplitude decreases, and we can suggest that this is because curved rods break uniaxial symmetry and they can't align coherently now under shear. So the collective rotational domains almost are smaller and less synchronized, and this will reduce this maximum amplitude of oscillations that we see initially. So essentially, the curvature frustrates this collective alignment and dampens this initial order parameter. And then I might just kind of skip quickly through now. I'm not sure how much time. I know we started a little bit later, but normally
It's fine. 20, so 10 minutes more.
10
I
minutes.
mean,
Okay.
it's really up to you, I guess.
I mean, I definitely have more things to speak about, but
That's
I
also why we're here.
yeah, I'm extremely aware of not really going over time too much. I want to respect people's time. So yeah. So and then a second parameter, which again we could see visually, but I like to really what's the phrase, hone it home or something like that with the fit, is that we can see that at this low volume fraction, if we increase curvature, we see that the frequency increases. And I kind of alluded to it earlier, but this is an aspect ratio effect. So as we increase curvature, the aspect ratio decreases. But also we can think about, at low densities, the collective interactions are weak, and the oscillation frequency is dominated by this single rod rotation dynamics plus kind of weak collisional acceleration. So Sorry. So curved rods, we can think about how curved rods have a smaller um like effective rotational inertia maybe, and then shorter Jeffrey-like periods under shear. They have shorter Jeffrey-like periods under shear compared to straight rods. And additionally, curvature-induced collisions will impart these impulsive kind of torques that could accelerate this rotation, and this will produce higher frequency oscillations. So I feel like I'm sorry, I'm certainly oversimplifying a lot of the dynamics with by comparing it to um, Jeffrey like situations, but there's definitely a coupling between these rotation dynamics and also the collisions even at these low densities. So I'm just going to flick past this for now, and then the reason originally we were doing this analysis is because we wanted to relate this back to our jamming volume fraction. So now we have volume fractions above and below jamming. So I've kind of taken a while to discuss what the dynamics of the behavior was at a volume fraction of 0.1. But now using these FIPS, we can get the steady state order at each of these volume fractions, and then we can relate this back to sorry, we can relate this back to the jamming physics. So importantly, kind of across all volume fractions, we can see that as we increase curvature, this uniaxial long axis order decreases. And we actually see, interestingly enough, a hotspot just below jamming for these small curvatures. And I don't think I said, but this dotted line is just the jamming volume fraction, just so you can really visually see what occurs just before jamming. So if we look at this slice in particular now, we can plot. There we go. We just plot the magnitude of the alignment against the curvature. I think at this point it is a little, maybe some might say overkill with this slice as well, but I just really want to show that as we increase the curvature, the uniaxial alignment decreases at a volume fraction of 0.4. So this is just below jamming. And if we do look at the director and dot this with the flow, we can see that for these small curvatures, this also shows that the long axis of the rod aligns with the flow, which is a dynamic, which is, a phenomenon which we expected, but we can surely show this. And if these two things are true, that the small curvatures align well, not only with one another, but with the flow, we can understand why we saw in the kind of the jamming volume fraction against the curvature, why the small curvatures will jam at higher volume fraction, because they're aligning well with one another and with the flow. Therefore, they can pack more efficiently and jam at that higher volume fraction. And then we can see that this long axis order is relatively isotropic for these high curvatures. And actually, I didn't show, but beyond 225 degrees, we no longer see a clear alignment with the flow. So we can suggest why this system would pack more inefficiently, as in higher curvature dense suspensions, and therefore jam at that kind of plateau of lower volume fractions. And then to build on that plateau, something that's so important when we're thinking about biaxial rods is obviously a biaxial biaxial measurements of alignment. So I've spoken a lot about the uniaxial tensor and kind of that primary magnitude of alignment, which was denoted SQ previously. Sorry, my notation has broken down there. That should be SQ. But we can also measure biaxiality, sorry, first via the uniaxial tensor. And I just wanted to show that what we can measure biaxiality via this eta parameter, and this is these two secondary eigenvalues of the uniaxial nematic tensor. And this quantifies the degree to which the particle orientations deviate from like perfect alignment along that single director n. So whilst the primary eigenvalue measures that uniaxial order along the dominant axis, the secondary eigenvalues capture this orientational ordering in the directions perpendicular to the main director. And that's why I just also wanted to visualize, I can show once more, kind of this is our flow plane, and then in the plane perpendicular, sorry, we can see that the long axis of the rod isn't locked into one clear director. So this is what this biaxiality parameter captures. And I certainly just wanted to kind of show that alongside the director, and then what these directors will look like in terms of where the biaxiality is. So what we can do is if we measure this average biaxiality against the curvature, where again these are just the steady state biaxial components, we can see that as we increase the curvature, the biaxiality in the system increases. So this further corroborates our narrative of if biaxiality increases monotonically now with curvature, packing efficiency will decrease with increasing curvature. I think I might skip through these slides about secondary biaxiality. If anybody wants to ask questions about the B tensor to measure biaxiality, I'm happy to speak about it privately or even in any questions. I just really wanted to talk about biological applications quickly, and I think I don't want to keep people too long, and it's a really nice way to end the talk. So please ask more questions about biaxiality if you have any later. But I just wanted to end this talk with quickly some biological applications. So sorry. So sickle cell anemia is a inherited blood disorder where red blood cells are abnormally shaped like crescents or sickles or curved rods. And this is due to the genetic mutation which affects the hemoglobin. And these rigid sickle-shaped cells block the blood flow, and they cause many things like severe pain, organ damage, chronic anemia. And people look at the system and look at the rheology of this kind of binary suspension with much more complex models than I have, where they resolve the cell membranes on a mesh or couple it with resolved hydrodynamics. But people also look at how blood behaves with just modeling blood cells with discrete spheres like I do. So a huge project that I'm undergoing recently is I want to look at binary suspensions of my curved rods and rings and see how different ratios behave in terms of the rheology. So here I've just shown, again, I think there's 25% of particles are visible, but I just model a bunch of different ratios of quote unquote red blood cells to sickle cells. And I chose these two in particular because these two had kind of my extremities of the phi j. So one of the lowest phi j's and a high phi j in comparison. So I model these three ratios, and then kind of the preliminary results I have right now are that if we look at the jamming volume fraction and measure reduced viscosity against volume fraction, we can show what the monodispersed systems look like. And then we see that as we increase the amount of healthy blood cells to kind of that one sickle cell, we can see that only a very low ratio of sickle cells does this system finally jump to the phi j of the monodisperse rings. So this was quite surprising because I think in actuality or in practice in hospitals, patients receive transfusions when they're kind of, I guess, a sort of sickle cell count is around 30%, and we've shown that it would, the ratio would be much smaller than that, and we would still see an effect and some jamming um, at these lower ratios, certainly than 30%. So I just wanted to highlight that work and say this is a huge project that we're undergoing at the minute to kind of resolve this further. So with that, just some quick conclusions about my work over the last few years. So we've seen that there's a non-trivial effect of curvature on the rheology of dense suspensions, and the jamming volume fraction as a function of curvature is non-monotonic. And we've kind of unpacked this by looking at both uniaxial and biaxial order parameters, whereby we saw that uniaxial order decreases with increasing curvature and biaxiality increases with increasing curvature. And we want to and are currently applying this to real life and biological systems where we've seen this kind of nonlinear mixing effect, where we looked at curved rods and rings. So with that, I want to thank my supervisory team and my CDT and my funding, and yeah, everybody in the department who helps me. And I'd also like to quickly inform anybody who doesn't already know or who could be available that we are having a rheology meeting at, well, mid-December, I would say, at the University of Edinburgh. So if you're around and you aren't aware of it, I just wanted to quickly share that is happening on the 15th to the 17th. So with that, thank you for listening. And I'll open the floor to questions.
Thank you. Thank you so much, Holly.
Thank you.
Yeah, thank you, Holly.
It was really, really nice. A really nice kickoff. Questions? What about questions? Maybe about biaxiality.
Yeah.
Emilia, please.
Yeah, Emilia.
Hear me?
Yeah,
Yeah.
kind of.
Talk. It was super, super nice and really cool simulations. Usually, yeah, it's super nice to see things flowing and more than just uh, in the accelerometer,
Yeah.
like with more picture way. So about the non-monotony, I had like a question that kind of links a few slides. So the question came up in slide 16.
Yeah, I can flip
So
way back.
it was a slide, I think the first slide where you talked about this non-monotony with the volume fraction that increases,
Yeah.
the jamming volume fraction. And the thing is that I thought, is it possible kind of to relate this result to the something you showed in like at the very beginning when there was oranges, bananas, and the work of the Oxford group? So basically, my question would be, we see that, for example, at low curvature, there is more efficient packing, if I understand.
Yes, yes.
So I'm imagining if there is some sort of vortex kind of assembly in a way that could take place. Because then I also imagine with the picture of the nest that you show at the very beginning, right? To like, I imagine if you had to construct or build a nest and you take a rod that's super no non-curved at all, maybe it's not optimal.
Mm.
You take one that's like completely is not optimal, then maybe like that system nature I don't know, brought this idea that maybe you have like an optimal curvature that allows some sort of assembly, and then the vorticity that you showed about the Oxford group. So I don't know if my question is kind of clear, but what about this?
No, I think it's a brilliant question, and I'm very happy that you pointed it out. I think what you were talking about, which is done, I believe, a lot in granular physics for certain, is kind of voids in these jam networks. And sorry, I lose my voice. Certainly, we have looked at quantifying packing, and there are a few ways to do this. And then we also want to look into kind of this, maybe the void distribution or even the void size. It's certainly something that we want to explore further. This was just something that we did primarily because they had a uniaxial axis, and we wanted to look at kind of the flow dynamics. But absolutely, if that's what you pointed out, I believe that would have a huge effect on the non-monoticity, the packing efficiency in terms of these voids, and and so forth. So yeah, that was a brilliant question. I hope I answered.
Yeah. It's really cool to kind of think about it, because indeed you could think that if the thing, like if your rod starts to become more and more curved or more
Mm,
close, it starts to resemble a bit more to a sphere or something that's basically closed, so it's
yeah,
harder to pack the space, right? So
yeah,
yeah, that's what I thought about. But yeah, also then I have a quick question about the biaxiality, because I'm not very
yeah.
familiar with this kind of stuff. But my question would be then, is it equal kind of to considering normal stresses instead of just a simple shear flow, and whether then there would be a triaxiality with like vorticity or something like this?
Um, Certainly a great question. I have a year left, and I think I had kind of a continuous variable of curvature, and then we kind of ran some simulations, and then we were like, oh, and what about this curvature, and what about this curvature, and this isn't just simple shear and different volume fractions, and already it was so rich and so much to explore. Sounds like I'm complaining. I'm not. I'm very lucky that the system is so rich, but yeah, I hope we could look at different modes of sharing the system, or different flow profiles, and see what other phases we would see, and certainly somebody else will have time to do that, but I don't think I will in the next 6 months or so before I start to write up. But it was a
Yeah,
great.
but it already looks like there's a bunch of yeah, results like you were saying. Then the just to like actually my question would be then if the biaxiality kind of is the same as normal stresses consideration in like the, for example, yeah, instead of simple shear. I'm not sure I understood that.
I'm not sure I entirely understand the question.
Yeah, if biaxiality is considering normal stresses rather than simple shear, right? Or is it simple shear in a different axis?
um hmm I would
Uh,
just I get what you're trying to say. I'm not sure I know the answer. I'm not sure if it's obvious to anyone else. I would think it's just the biaxiality of the alignment in terms of what I spoke about with the uniaxial measurement, and those secondary eigenvalues. I would think that was just still a response to kind of the shear as opposed to the normal stresses. But
okay.
I'm not entirely sure, actually. I'm not sure if it's an obvious
Yeah,
answer.
I think my question is a bit messy because maybe just to put it a bit more simple, the question it would be if the model is considering simple shear. Yes, right. Uh,
Yes, yeah, yeah.
okay. I think it's a bit more clear for me. Thank you. Thanks a lot.
Thank you. Thank you for the questions.
Thank you. Is there any other question in the audience?
Yeah,
Yeah,
Joshua, please.
Joshua.
Yeah, I have two questions actually, Ollie. Great talk.
Thank you.
Because the rods they are stiff, right? They don't deform.
They don't deform.
And is that a limitation in your comparison to blood cells, for example? Because
Yeah,
they're very soft, right? So
I I love that question. It's not a limitation per se. I think it's just an oversight for now with some kind of quick preliminary results. We can relax the harmonic potentials in the quote unquote, healthy blood cells, to make them
Mhm.
more flexible, as is, physically accurate. But I think we just kind of allude to that system for those preliminary results. I think it would be more accurate to also have, a red blood cell that wasn't hollow. So if we wanted to look at it further, and if we had a specific question in mind that didn't relate exactly to our configurations that we've looked at here, we can. I would say it's a limitation of the model. I'm just not sure how much light this model could shed in comparison to those which are so much more complex, if that makes sense.
Yeah. No, but it's especially interesting because of I think, the sensitivity to the curvature, right? So even a
Mm,
weak curvature will give you already an immediately different jamming volume fraction, for example,
exactly.
for the Rod's case. So,
Yeah.
and even weak driving can already, on average, bend the rods a little bit.
Yeah.
I suspect so. And that is also then related to my next question, which is the effective friction coefficient that the rods have, right? Because the rods are, as I understand, just connected spheres, no?
Yes, they are.
And I can imagine that if you make a rod with a slight curvature in it, that essentially would act as a straight rod, but just with a slightly higher friction coefficient, also uh, doing something with the jamming volume fraction or the overall dynamics in the first place, right? So it's really difficult to disentangle the effective friction or the effective interaction based on curvature versus based on the the friction between the rods. Have you thought about this?
I have thought about it. I think I can't remember. I think Michelle, it was one of your friends maybe in the granular conference. I think I remember somebody specifically having this conversation with me. I am aware that you can't disentangle that effective friction coefficient and that it's not quote unquote accurate physically for a single sphere to be in contact with those two other spheres and what the resultant friction would be. So we've definitely thought about it. I think a few people have done kind of these like what's the word? These discrete sphere models and tested, contact forces. Maybe I could try and disentangle the two with some, benchmarking simulations. But it's something I've thought about, but I don't have a clear answer for how to entangle the two or what I think the effect of this effective friction is on the rheology that I measure, if that answers your question.
Yeah, well, kind of, right? Because and I'm thinking you also don't necessarily need to disentangle the two things. Maybe everything or some of these effects can be all understood in terms of just an effective friction
Right.
coefficient. Like because there a friction coefficient, I don't even know what it means anyway between two spheres, whether they are rough or smooth or lubricated or whatever. There's some effective way of modeling that coupling between normal and shear forces on a particular particle and how that then generalizes to even rod-like particles or so, it's entirely not obvious. So better just to see it as an effective coefficient, and then perhaps your curvature can just simply map to an effective, slightly different friction coefficient, which would, for me, conceptually simplify the problem. So, but no, I think it's an interesting thing, and I wonder, like, in your simulations, if you crank up the friction coefficient between the individual spheres, because I'm sure there is one,
Yeah.
could you push it somewhere else, right, in phase
Yeah.
space, and then effectively enhance the effect of curvature, perhaps, or decrease it? I can imagine that, for example, at a higher friction coefficient for the spheres, your weak curvature effect goes away entirely.
Yeah, I think it would be the only issue with my simulation, and it's worth pointing out in case somebody else models anything similarly, is that I have to maintain a high kind of friction so that the rods can't roll past one another because that affects the dynamics. So because I use lamps, it would be a little bit difficult to maintain that, intramolecular friction. I think it's not clear to me how I would do that. But I'd have to maintain that intramolecular friction, especially for the straight rods, so that when they align with the flow, they don't just roll past one another. I hope that kind of like train wheels with two plates either side in different directions, and then they never rotate with the flow; they just stay aligned. So that's unphysical. So actually, in terms of the friction coefficient, that stops them from doing that. So my first hurdle, I guess, would be keeping the friction coefficient high enough so that they wouldn't roll past one another, but then also being able to vary it. So I can see, like you said, if we see the same function with jamming volume fraction, if we vary this friction coefficient. But absolutely, really great suggestions. Thank you.
Yeah, nice. Thanks. Thanks, Hans.
Thank you
Thank you.
for the questions. Any more questions from the audience? Yeah, please.
Hiya, thank you so much. Sorry if you have already explained it, I may have missed it. So when you have particles that are made of spheres that are, I would say, large relative to the size of the whole particle, do you think or have you studied if uh, the roughness that's induced by having individual spheres attached together would affect the things that you observe in your simulations? Like if instead of having 6 relatively large spheres, you had 60 smaller particles, do you think it would change the results that you see?
I just want to make sure I'm certain that I understand the question. I'd say
Yes.
first of all, kind of the relative size to one another is
Mhm.
doesn't matter if the aspect ratio is the same. So if I had 10 times more particles that were 10 times smaller, then it would be the same um, function and the same system if it's an aspect ratio effect. But what I didn't know if you meant, but is an interesting point that people have looked at certainly in other systems, but I haven't in mind, is that you can look at if the particles overlap with one another, to what extent does that approach kind of the straight rod or a curved rod dynamic?
No, sorry, maybe I did not explain it very accurately. So instead of having just 6 particles, you can have 2 layers of particles, for example, having 12
Ah,
particles, but
um,
by adjusting the all the dimensions and then adjusting the roughness of the whole particle by that, do you think if you had this freedom to adjust the particle size in all dimensions, it would affect the results that we see because of its
yeah,
effect
I
on
think I know what
the
you mean.
roughness?
I think I know what you mean, but again, I'll just kind of walk through what I think you mean. We do have the freedom to do that. The reason
Mhm.
we use 6, or you could use however many, beads you wanted, as long as the aspect ratio is the same, is because it's cheap and we have a really
I
dense
see.
system. We have thousands of particles, and then we're
Yes.
calculating every time step lubrication forces, contact forces, etc., etc. So it's already computationally quite expensive, and we've already kind of jumped through a few hoops to make it cheaper. So certainly in other systems, people will almost what I think you were suggesting, which is kind of resolve, the shape more
Yes,
accurately.
exactly. Yes.
People do that, and it's a great suggestion. The reason I don't is simply because it's cheaper.
I see. Yes, you're right. Thank you very much.
Yeah, thank you.
Thank you. Is there any other questions? Oh,
I do have a couple of maybe curiosities more than questions actually. Um, so one is you almost answered it a second ago. How many particles do you have more or less in your system? I mean, how big is your system? Do you choose the box size or the number of particles?
I choose both, so it's 6,000 particles.
6,000. Okay.
It's not huge,
Well, it's quite a lot.
but it's pretty big. Yeah.
And sorry, and when you say 6,000 particles, you mean
One,
beads?
yeah, so 1,000 rods, because there's always
So
six.
1,000. Okay, perfect. Yeah. Okay.
Yeah.
And okay, the other, I have three very tiny questions. Slide, well, let's start with slide 16, or I mean, slide 16 just because it's there. When you compute when you evaluate the jamming volume fraction, how do you do that?
So, as in terms of this figure as well.
Yeah.
So initially we wanted to use the fit of like a Krieger Doherty, but I think that's been evaluated for straight rods, but is initially a model for spheres. The fits um just weren't good. So instead we just look at the 2 points with the highest gradient. So kind of the divergence in that curve based on those 2 points. So it is something that is reliant on the resolution of the simulations.
Okay, so you haven't really tried models like
No,
I
we've
mean,
not.
they're for spheres. I know. I was just curious if you tried.
No, I think it would be great to have sort of I think maybe we just kind of skipped to what was cheap and cheerful at the time and said, oh, we can just find the highest gradient and that's the jamming volume fraction. But it would be nice to look at expanding a Krieger-Doherty like equation
Yeah, I
to
mean, I really have no idea. I mean, I don't know what people do in this community with rods. Maybe, I mean, I would suppose that, I mean, for sure the exponent would be different, or maybe also
yeah. So I think
the
the exponent is different
yeah,
for rods in comparison. Like I think it's the beta exponent is different. Um,
yeah, exactly.
but it
So I
didn't.
mean, yeah, okay.
Yeah, but so
And the other question is also related to kind of to this figure, but it's a bit more clear in the previous one, so in slide 14. And again, with just spheres, which is what I do, I'm used to see the oscillations of the viscosity increase with the volume fraction, while here it seems that the highest volume fraction has the lowest oscillations.
do you mean kind of like the noise, I guess?
Yeah, yeah.
Um, I agree with you that that's true, but I have actually never seen, or I have not, I've never modeled with my system just spheres. So
It's funny. I mean, I'm not
yeah.
saying. I mean, I
No,
trust.
I know.
I trust the data, of course. I'm just saying that it's
Well,
interesting.
is that true? Because I would think that, I mean, if we're looking at kind of the noise at higher reduced viscosities, it would be less so obvious in if we think about kind of the error in relation to the value of the viscosity.
Yeah.
I think it would be less. So I would think that it would be we would see more noise at lower volume fractions because the value is smaller.
Well, again, that's not usually what you see with spheres.
Oh,
With spheres, it's really if you compute the variance of the viscosity, it really just goes up with the volume fraction.
oh well, I might take a look at it. I didn't know that. That's an interesting
So
point.
it's just an interesting quantity to
Mm.
measure, I think. And and then a comment about the work you've done at at low volume fraction, so
Yeah,
at
that's it.
10%. Uh, do you trust it?
Yeah.
It's a provocative question, I know. I mean, but
No,
you
no, it's a
said
great question.
you said it yourself. You don't model, you don't compute long range hydrodynamics, and at 10% you're pretty dilute.
So, um, yeah, absolutely. It's provocative, but it's a fair question. I think that we quickly looked at kind of with our system, what does the Jeffrey orbit of one rod look like, and it converges to what we see um, in a more complex model or in reality, and then from that, I just kind of jumped into the deep end and said, oh well, we see this, and is it Jeffrey orbits? Is it this? Um, Certainly, if we were to take this further and publish it or look into it more deeply, I would have to prove that certainly the model is capturing everything you would physically expect at low volume fractions, with it being so minimal. But
No, but I mean, 10% volume fraction is very dilute for spheres. Again, you have rods. I
yeah,
mean, it's a totally different situation. So
yeah,
it was provocative, but also a very honest question. Uh, so you definitely have more context with
yeah,
these rods than with spheres. So maybe the contribution of context, even at 10%,
yeah,
is enough.
is enough. I also will say quickly that there's several works by I remember only like the first author who's S. Teedle, maybe at Georgetown or somewhere, and they have a completely different model and they look at long aspect ratio rods. And they also, in one of their papers, reported on these oscillations, but didn't, well, from what I read and what I remember reading in the paper, kind of go into any detail as to why they occur, or they just kind of reported on them. So certainly, if like you said, if it's kind of an effect of these rod-like configurations, then it could be physical. But I'm definitely taking it with a pinch of salt right now. And um,
Okay.
yeah,
No, that's very cool, by the way.
thank you,
Thanks so much.
thank you.
Okay.
Yeah, thank you very much. I just have like one just curious. Oh, there is a question. Go ahead. Sorry.
Yes, hello. Can you hear me?
Yes,
Yeah.
Perfect. Thank you for the great talk. It was very nice.
thank you.
So I think I have maybe a question on slide 16. I think it's 16. Yes, exactly. So maybe it's a weird question, but okay, if I look, for example, at the green one, so the circular one, and I imagine if I break it partially, then eventually I can get a curvature that is like maybe the purple one, for example. So my question would be, imagine that you can break it. I know you can't break it normally, but imagine you can. Do you think that you could dynamically go over your graph? So you have a jamming volume fraction, and then you break it and you change the volume fraction of jamming. If my question is clear.
I think I know what you mean. But I'll just kind of propose something to see if this is what you mean. Did you mean the kind of, well, I mean, you could have meant either, but you said green, and unfortunately there are two greens.
Yes, sorry, light green, yeah.
Light green, and then it would be purple. I guess your question by break is kind of like, is it if it was deformable? So if it wasn't, stiff in this shape, and then therefore if it did deform dynamically, would that jamming volume fraction shift in real time? Is that the question?
So that could be a variant of the question, but the question is rather, imagine that you cannot deform it, but you can break it. Then eventually by breaking some parts, you can get another curvature. So for example, for the right-hand side, extreme right circle, if you break it in half, for example, imagine that you can get some curvature of the others on the left, if that is clear.
I think it makes sense. I'm not sure
Yeah.
it's doable with my model with the harmonic potentials. So if they were pushed out of whatever the harmonic potential, so if it's too far from equilibrium, the system will quote unquote blow up, so that the simulation will fail. So
Okay.
they can't be broken in the simulation. So certainly I don't have the capacity to do that. But absolutely, if you had, experimentally rings and they were to snap, symmetrically, they would form two smaller curved rods then, and then yeah, sure, there would be some maybe nonlinear mixing effect again with the viscosity, but I wouldn't be able to do that, and I'm not entirely sure what would happen in terms of
I see.
but
I see. Yeah. No, I know that my question is a bit not answerable, but I wanted to ask it in case you.
no, it was a great question, and I think when we look at complex shapes, everybody's quite imaginative with what could happen and what you can look at, and that's a great part of the stuff that I research. So no, it was a great question. Thank you.
Perfect. Thank you very much.
Thank you.
Thank you very much. Is there any other questions? I think like we had already a lot of questions.
Yeah.
Maybe we can send all of the questions to you after the talk, because it's already a bit late. I have just one tiny question because I'm not at all in that part of rheology. But I was asking myself, like, what if you have those rods but as a S shape, and you take the same theta? Do you, for example, let's take the brown one, and you do the same part on the other side? Would you have something that looks like the more or less like the blue one or not? And then you can change maybe the flatness of the A shape. I don't know if you have tried that before.
I think again, it's a
Yeah.
great question. I would be able to do that because it's just you would have to change for kind of the flip, so you get the S shape. That's just the dihedral. It's like kind of like a cis trans transition, which is what we kind of refer.
Yeah.
Yeah.
Exactly.
So we can do that, and then if you wanted to vary the flatness, that would just be your bond angle again. So certainly you could with this model create those configurations. I wouldn't think that it would approach, certainly for like 6 particles or aspect ratio 6, I wouldn't think that it would approach a straight rod because they'll rotate
Yeah.
because they have that biaxiality again.
Exactly.
So I wouldn't think it would be a straight rod. I think it would be rich in many ways again in terms of they would interlock, they would have to align in certain ways. And if we're looking at shear flow, they would align with the flow. So I think people have modeled, or sorry, not modeled, people have experimentally looked at staples and how they behave in these systems.
Mhm.
So that reminds me of that work, but I haven't done so
Yeah.
yet. But it was a great question.
Okay, well, just to know more. Yes. Okay, thank you very much.
Well, I
Michelle,
think
yeah.
that's clear that there is a lot of things that you can do with your project,
Yeah.
and that's always great news. Thank you so much again.
Thank you.
I guess we can wrap it up here.
Yeah.
And again, that was a great talk. Very nice start for this fourth edition. And thank you also for accepting kind of last minute to give this talk. And thank you also everyone who attended. That was great. Thanks for the questions. Thanks for being here. We're gonna see you in 2 weeks for a class
Yeah.
by Anke Lindner. Don't miss that. And other than that, thank you again.
Yeah.
Thank you very
Absolutely. Thank
much.
you so much for everybody's attention, and thank you for all the questions. And thank you again to the organizers for inviting me.
Thank you. Thank you.
Thank you, Holly.
Good
Thank
stuff.
you.
Cheers.